Hello, everyone. We are back here again. This is Nicolas Vasiloglu, VP of Research ML at RelationalAI, and this is the long version of my presentation about trends in machine learning at ICLR or ICLR 2022. This is going to be part one. And then we're also going to have a sequel with a part two. So not so long ago, ICLR 2022 took place virtually with many papers published. You can find on the website the exact number of papers, but it's in the order of hundreds. We spent a lot of time going through most of them, and these are kind of like some keywords that emerged after reading these papers. We don't have any surprises. I believe what you see over here is things that you've been hearing all around. Things about distillation, diffusion networks, and neural ordinary differential equations are fairly recent. But there are some new terms like Mixup, which is a new way of self-supervision, which we saw in the past 2 years, and it's becoming more and more popular. The backdoor attacks, attacking models, and like a lot of security issues are emerging on the academic level. We haven't really seen them in practice yet. Surprisingly, a lot of papers about molecular protein and drug design with AI, kind of like riding on the way of AlphaFold 2. And of course, the king and the queen of the conference remain self-supervision and language models. So if we had to summarize ICLR in a nutshell, we would say now, we've experimented and we studied self-supervision well enough, even at theoretical level, so that we know how to apply it on every type of data and every type of network. So ranges from text, images, now tabular data, graph neural network architectures, graphs. So this is something that we see it, a lot in the conference. Of course, we see other things, but this is something that I'm kind of like I kept from the conference. Now, these are the topic of interest. I'll talk a little bit about how we did this presentation. We talk more about that in the blog post. But as we were reading the paper, papers, we kind of like settled into these categories, taxonomies. We're not going to go deeply on every category. My view is biased towards language models, self-supervision, a little bit about vision transformers or sparsity. And of course, we always get excited when we see a new idea or a new paper that touches on the fundamentals and the basic principles of machine learning, which we all kind of like consider or given, and they don't really change that frequently. That's why they call it fundamentals. So my disclosure is that a lot, obviously the content is vast. It's it took about 100 hours to go through all of them, and I just want to talk a little bit about the process. Typically the papers are, I see that as a trend. They're trying to make a very clear statement with their title, so they try to be very direct and blunt about what they're going to say, not very cryptic. So they want to surface the message so they can attract their attention, because there's a lot of information clutter in literature. Now, so that's a good thing. And then the next thing, if you have to go through all that content, is you need either a figure or a bullet list or some kind of like a paragraph that really gets into the point and gives the basic hints and the explanations you need to understand it. And that helped a lot with papers that had that. Unfortunately, there were other papers that they would require more time to get to the message, and we had to skip them. But it's good that the community sees that and tries to be as clear as possible. Now, in this part one, we basically going to talk about self-supervision and language models, just because there were a lot of papers there. And you see my the subtitle called Mixup, because this is how I'm going to start with a Mixup, which is a very common self-supervision technique. I think it started 2 years ago. Last year were a lot of papers, and you know, this year papers keep referring to it. So I'm just gonna refresh a little bit what we mean about with self-supervision or data augmentation. You know, we are all used to this supervised model where I take labeled images, I pass it through a network, and I train a classifier. In self-supervision, you take unlabeled data and you create the labels by just doing a transformation of your data. One common one is that you create a jigsaw puzzle of the image, or you take a rotated image and you're either trying to find out how to fix the puzzle or find the rotation. Okay, and you can generate unlimited data. So what happens is that you train the network finds the interesting part, becomes wise, and then use a few labeled images to run your classification. You typically get better results, compared to just going supervised from the beginning. Now, Mixup is a data augmentation technique that it doesn't act on a single, usually in the images, you take the image and you rotate it or you permute the jigsaw puzzle. But it takes 2 points, and based on the 2 points creates a third point as kind of like a linear combination, convex combination actually, between them. And you can do the same thing on the label, if you want. Now, very, very, very successful. You can find a lot of papers talking about that. But this paper doesn't say, there's a simple trick. It's just like instead of doing the mix-up on the original points, you do the mix-up on some noisy points. So you add some noise. So you pick any point in this ball here and point on this ball, and you find your new mix-up point. And I think we're used to that. Noise has proven to be very effective in machine learning. Differential privacy is one case. And of course, we don't forget the stochastic gradient descent, which is one of the cases where noise turned out to be very beneficial. There is a paper that explains here, when and why mixup works. So that doesn't always work. And I think here you see this mix-up, how much you're mixing them can, if you don't mix them too much, then it doesn't work really well. This is kind of like an octuple mix-up, and then it starts kind of like breaking. So there are limits. Now, there's another paper that talks about something we sort of have forgotten a little bit about it. It's called the one-class classifier, okay? And here's a little bit a different problem. It's called positive and unlabeled learning. So we only have positive labels and a lot of unlabels. And usually what we would do is we call it contrastive learning, and we would treat the unlabels as negatives. This paper is actually using mix-up close to the boundary in order to improve the solution. So this is kind of like another revisiting of the fundamentals. Then again, once we introduce a new technique like augmentation, we realize that there's always limits and boundaries to what we're doing. So for example, there's several ways to create augmentation. I talked about the rotation, the jigsaw. Sometimes, they're trying to take the black and white or the grayscale image and predict the color one. But, not all augmentations are beneficial for training a network. They have to be somehow relevant to what you want the network to learn. So this is a paper that creates a reinforcement learning agent that basically tries to learn, to find the policy for learning the right data augmentation. It's called like difficult, but not too different. So it's trying to make it difficult, so kind of like modified it as much as it can, but it doesn't want the two augmented instances to be very different. This paper addresses exactly the same thing, and instead it used a deep neural network that's trying to decide what's going to be the next augmentation. So this is actually doing the augmentation in sequence and trying to find the right sequence of augmentation, one after the other. Very interesting papers. Now, you know, if you kind of think about it, dropout is a way of augmentation that's like kind of like on the network. Okay, so dropout, for ability, if you don't know, is like during the training you tend to drop some weight, some connections, or set them to 0, and that helps the network learn better. Now, what happens is, you know, now we tend to use a lot of neural networks that are actually tiny, small. You use them all the time on your cell phone, on your on any edge device. Any edge device is using like a tiny ResNet or even language models. And what happens is that when you train them, you cannot afford setting weights to 0 because you really affect the performance. So they do something that I call, it's not on the paper, I call it like reverse dropout. So you take your network, you make it a component of a bigger network, okay? And you train your system. So you basically train with more parameters, you make, and then you take that out and you fine tune it. And it turns out that it learns really well. Okay, so that was a very smart idea. I really enjoyed reading that paper. Now I want to go back to, and I should have had a reference to that paper, a more extensive one. I felt like I had too many slides. SimCLR was was a revolutionary paper in self-supervision. So basically, the idea is that you take an image, you run two different augmentations, and you want the representations to be as close as possible. And if you take two different images, you want their embeddings to be far away. Like, it's called contrastive learning. Now, it turns out that if you do something like that on ImageNet, which is self-supervised, because you can choose whatever augmentations you want, you know, train your model and then do some fine tuning with, I don't know, 1% of the labels or 10% of the labels, you end up getting much better metrics than if you were just like training from the beginning in a supervised way. Okay. Now, people are doing the same thing for tabular data. Okay, so here we learn how to do self-supervision on tabular data, kind of like a hint. The idea is that the augmentation there is randomly changing one element of a tuple. And usually the way that you change it is by sampling it from the distribution of that column. So if you have ages, for example, and one of your feature is like the age, you randomly flip it into one of the ages that you have in your data set. Okay, and apparently that technique, that self-supervision technique, has very good results. Now, you probably didn't know, I didn't know, as I was reading that paper, there's 5 different self-supervision techniques for graphs. When you see SSL, don't confuse it with the security term, but it means self-supervised learning. So here's kind of like another paper we saw before for writing finding the right augmentation for GNNs. We don't have time to go into meta learning, but this paper makes an interesting connection between contrastive learning and meta learning. If you're a practitioner, probably wouldn't matter that much to you, but in a nutshell, if we build a classifier with each data point being a label, you know, how well does it predict distorted versions of that point? So in meta learning, you know, each point is a label, sometimes called like zero shot. And here you can look at the paper. It's really like, you know, these two diagrams are very, very similar. Kind of like that part over here is replaced by this component in meta learning. Now, something else that we hadn't really realized, that adversarial learning is another form of self-supervision. So, you know, this is kind of like a follow-up to a paper that was published a year ago. So I'm going to skip that paper and tell you what the original, because it's kind of like an incremental improvement of that. But so that was actually 2 years ago. It's called Electra. And the idea is that, you know, you have this mask language model where you're putting a mask, and here you have the predictions. Now, you're having another network that sees that as an input. And it doesn't know whether these, like the, chef, ate, the meal, like which words were predicted by the transformer and which ones you actually put them as an, you know, in your input. So you're training a discriminator that tries to find out whether this or, you know, which word was original and which was actually replaced on a mask. Okay. Now, if your MLM, mass language model, like your BERT, is trained really well, the discriminator shouldn't really be in a position to figure out which one is a prediction and which one is the original. So you know what I'm saying. Now, this is adversarial training. You're basically training it in a GAN style, in adversarial way, so that you know, the discriminator in the end has like 50% accuracy. Like you can predict whether something is has AUC 50%, cannot really predict, you know, discriminate whether something is a prediction or original. A very clever way, in my opinion. And apparently, we talk about that here because you see that training with Electra gives you kind of like better results. Now, so supervision is great, or constructive training, but sometimes it goes south, and there's kind of like catastrophic effect of collapsing. So what happens is that you know, in the complete collapse, all the points kind of like collapse together, or in some cases they collapse into a hyperplane, and that is a problem. So that paper talks about how you can avoid it and how we can understand it. A great paper. Again, the theme over here is like trying to learn how to self-supervise everywhere. This is self-supervision over databases. So basically, how do you train a database in a self-supervised way, where basically you have a query and you're trying to predict the output of the query. And you know, that paper goes through how, you know, how you can do it. It's not super practical because in the end, you know, it assumes that you have a query, like you have to send to the language model the whole database, like that table can be big, and the query, and it reasons over that. So it's not really practical for big databases. Okay. Now, on the contrary, this paper is actually very practical, because if you are working on practical problems, you realize that sometimes this is called weak supervision. You know, let's say that you're trying to predict lion, wolf, dog, or cat, like these 4 categories. And in some cases, you have that label, but in some other cases, you have a different label which is related to that label. So you might be able, through some rules, to extract whether this is like a Bengal cat, which, you know, there's an ontology that tells you that a Bengal cat is a cat. Or in some cases, you might predict that it's a wild animal, so it could be a lion, or it could be a wolf. So, you know, how can you use that information, like, which is kind of like incomplete, but sort of related to your label? So you basically have an ontology, and you need to include in your self-supervision that ontology to get better results. And that's a great paper that describes how you can do that. You know, another kind of like surprising result. So there's a lot of kind of interesting. I want to say they're trying to take it to a theoretical level, but it's an empirical study. Is that if you just like stream your data in the pre-training of the language model, that's sufficient. So you don't really need to have all the data in the beginning. So they call this joint training if you have everything in the beginning. but if you stream them, it helps like a better capability of overcoming the catastrophic forgetting. And there's a hypothesis that the sequential self-supervised learning have flatter minima than the ones that you join all together. So anyway, it's kind of like an interesting finding. Now we're starting exploring a little bit the boundaries of self-supervision. Now another thing, I think we all got amazed with the GPT-3 results, where you run this extreme self-supervision session, and then maybe you fine-tune in the end, and we kind of think like self-supervise for long and fine-tune for a short time, maybe zero shot. Well, this paper talks and does a more thorough study and says, well, if you know your end task, then don't pre-train forever. Like, start introducing your end task fairly soon. Okay, don't wait for that long, because you might pay a price in the final metrics, in the accuracy. Another interesting paper is, how do you train, pre-train two different modes at the same time? So it's using different attention and cross attention heads between images and text. And it has like this nearest neighbor. For example, you can train this image with this caption, but then you can look at the database and find another caption that is similar to this one. So you can actually, associate this with this and pre-train it, and that gives you much better example. Something that we're going to see later on in another case. And here's kind of like a very impressive paper, in my opinion. If you've been in the area of data science the past, I don't know, 12, 15 years, you remember all these techniques that we used for dealing with imbalanced labels and data, and all these problems you had of some catastrophic effects. Now, somehow we forgot about it. But it turns out that, we used to use a self-supervised technique where, so very trivial, you just like copying and repeating the lowest represented class. You can see that as a self-supervision. But apparently, the self-supervision techniques that we've been talking about, they have another, positive side effect, which is that they really work well with imbalanced data. Okay, so apparently, because the model learns the right thing, it's not sensitive. And here you see the gap relative to a balanced data set, and in self-supervision techniques, you see that the gap is much smaller as the blue one. And the paper gives some, it's kind of like an intuitive explanation. You can, if again, so that I did, like, if you read the caption on the image, it will be easy to determine how and why. Very happy to talk about that offline. We talked about weak supervision before. I forgot to mention that was mainly from Snorkel. This is another kind of like Snorkel type paper where traditionally Snorkel was for classification. Now they extended for structural prediction, regression, and ranking. And that's kind of like a simple technique. They have a framework about how we can basically extend Snorkel for other types of problems. Okay, so here's a list of all the papers that we talked about. You can click on the links and go to the original papers. Okay, and now we are going to move to language models. So, more transformers. In a nutshell, transformers become more scalable, more predictable, more expandable. Now they become editable. And in my opinion, what has helped achieving these properties is the emergence of vector databases. Okay, so we're going to see how this is helping them. So this is the perceiver from DeepMind that created a lot of buzz when it came out. And the main idea is to reduce the complexity by using less vectors of self-attention. So, you start with a latent array. It's kind of like clustering the one side, the n by n matrix, the one matrix, the one, and you're trying to make it smaller by learning some latent vectors. So basically, instead of attending everything to everything here, you are trying to find a smaller number of vectors to attend. And the other thing that they also introduce is that, if you want to define the task that you're trying to solve, usually you do it with some instructions that you put in text mode. For example, translate this, or complete the sentence, or something like that. Now, you can do that by, you can encode the tasks into vectors, and surprisingly, that compresses the network and makes it more scalable. Now, one of the things that people are criticizing the language models is the ability to correct facts that the model has gotten wrong. Sometimes we know that can raise ethical issues about social biases and stuff like that. Now, I don't want to go into the details, but you basically simulate the learning. The gradient descent can, if you write a gradient descent, let's say 5 steps ahead, this is kind of like differentiable. I mean, the main idea is try to fix it without having to compute the full gradient and run an update that it's slow. And also make sure that as you're fixing this, you're not messing up something else. So don't fix one fact and because you fixed that, you made something else wrong. Now, this is a big challenge the paper is trying to addressing. In my opinion, it's not fully addressed because there's no way you can check whether you have to prove that you haven't messed any other facts. Okay, so it's not like in the database that if I change one fact, I know that it's not affecting, something else is going to become true or false. It's much easier to prove it symbolically rather than in the continuous domain. So, another thing we talked about earlier, and that paper seems to be in the same spirit that, just throwing more data and pre-training more and more doesn't mean that you're gonna improve your downstream tasks. In some cases, just collecting more labels and using less data can give much better results. So again, in the spirit of pre-training, is not always, it's not a panacea. You cannot just use it uncontrollably. Now, remember when we talked about this paper where I'm training 2 modalities of an image and a caption, and sometimes, I replace the caption with something else similar that I find in my training data. Apparently, the same technique, you can use it when you have text only. So usually, you encode part of the text and then you're trying to predict, I don't know, the next 5 or 10 words. Okay, but great, that works. But sometimes if you just take the next 10 words you're trying to predict and look into your training data and you find something similar and you replace it with that, apparently you get some huge, you see the curve over here. You start with a regular pre-training and then you kick in the KNN pre-training, which means that you are replacing your target with something textually similar, symbolically, cosine distance, something like that. And that, start jumping and they report some, impressive results. Like in the QA score is 5 times better than before. Of course, we talked about tiny transformers, and this is the dict former, which uses dictionaries to share weights. Here's kind of a diagram where basically you can achieve, like you can have everything. Like, because typically the more parameters you had, the better performance. So this is kind of like a universal transformer, and the dict former combines the best of both worlds. So you get everything. Okay, that's an interesting paper. It's one of these papers that when you read, transformer has this capability. There's some cool demos, and they work in cases where you don't expect. So they use transformer to learn concepts that they're not necessarily in one dimension, they're two-dimensional. So it can learn the left-right, it can learn the north-south, or the colors. You can give the RGB and it can tell you what color it is. Basically learn that. And here's, I'm just going to focus on one example where it learns the left and right. So, in this world, this is right, this is right, I don't know, this is left. And here you present this world that it hasn't seen before. And it does really get that this is, you see GPT-2 doesn't really get it. But GPT-3 really gets it. And it does get that, this is left. Again, interesting. We came across this paper as we were going through as a reference. And it's not an ICLR paper, it's from a different conference, but it was a reference. And I find it really interesting that you can create an ontology from a language model. So you start with these facts, you extract this, these entities, then you create a graph, and then from that graph you get into a tree. Yeah, that's kind of like an interesting paper if you really want to generate really long sequences. Like, you need to know where you want to start and where you want to end, and then you create an interpolation and a random walk, like a stochastic process that helps you create coherent text. This is kind of like the holy grail of one of the holy grails of language models. Is called the 1-bit BERT, or the BBERT, where you basically want to have like all your coefficients are binary numbers, 0, 1s. And that has obviously tremendous advantages in terms of porting that to hardware and being fast. The problem is like, how do you train it, and how you binarize it, so without losing accuracy. And well, this paper talks about some kind of like distillation techniques that can get you there. If you are an ML engineer or an application developer in databases, you are familiar with the terms of incremental maintenance. Okay, so if you have a knowledge base, keeping it up to date, deleting facts that they're wrong, and updating facts, it's not an easy task. And in the symbolic world, you probably have to do that manually. It's not easy. Now, with language models, what this people really did, it was like they created a benchmark, where you're changing the facts. Like, Obama was a president, and then it was Trump, and then was is Biden. So changing, you don't really want to keep training from scratch every month your language model, because most of the facts are not going to change. So that paper touches that that subject about how you can do it in a continuous. You can find it as like continual learning. It's another term that you can see. Okay, so here's an interesting paper, and I think it's interesting because it makes a claim that another paper and the same conference makes a counterclaim on that. So almost a counterclaim because they're solving almost the same problem. So if you want to reason over a knowledge graph, you can use a language model where you're feeding as an input the knowledge graph. How do you feed it? Obviously with a GNN, and then the proposition you're trying to answer as text. Okay, and this is I feel like this is a pretty straightforward architecture. There's nothing difficult over here, and they report some interesting results. Nothing surprising. We're going to see later some counter arguments. That paper is basically trying to make an attention layer that works in 2 dimensions, like in 3 dimensions, like a video. Like think about a 3D attention. Straightforward, of course, a lot of computational issues, but the authors deal with that. And this paper over here talks about another self-supervision from text generation with Mixup. So remember, usually when people are doing self-supervision, they're self-supervising on the input. So you have an input task, you put a mask layer, a mask token, and you're trying to predict the mask. But here what happens is that you're using an encoder, what's the weather today? And then in the decoder, you know the output, so what has where it is, and then you're masking the sunny over here. Okay, so you're basically doing the self-supervision on the target. That's what it is. According to the authors, you get better results. Okay, and obviously that applies to model encoder decoder models like T5, for example. Okay, so this is kind of like a next generation transformer. So it has the whole idea is that the number of heads is kind of fixed, and that's kind of a problem if you want the heads to have some physical meaning, and you really need to make it dynamic, how many heads you're going to have and how many heads you're going to use. So anytime in deep learning you want to select or make active part of something, you're using attention. So as you guessed, you're basically using an attention layer over the heads. So attention over the heads, they're already attentions, over the number of heads. So basically which heads are going to be active. Like if you remember the transformer, in the end, you take all these heads and you concatenate them. So it's a concatenation is an aggregation. Now you concatenate them or you're aggregating them, but you're putting a weight, and where is this weight coming from? From another attention layer. Again, that helps transformer. Every time you're introducing something that is learning, something which has a physical meaning, has a concept, you end up getting better results, and that's the case over here. Okay, so my initial statement was that transformers have become more ready for production. So people have seen instability. So if you're asking for a factor equation, a question from a transformer, if you ask it different ways, you get different answers. In fact, there was a very recent paper where you ask a question, like it's a reasoning question, you're getting really horrible performance. And then if you just say, let's solve this step by step like this, then it jumps tremendously. So the idea over here is more or less the same what compiler people are doing. So it does a rewrite, so they introduce an intermediate layer that tries to standardize and always bring it in a specific form, so that no matter how you write it, as this P adapter, as they call it, it's surprisingly it's a bi-LSTM, which we haven't really seen for a long time in transformers. I don't know why they chose this architecture. It does seem to work, but I like the spirit of making a rewrite that stabilizes things. It's in a good direction. It's very practical. That thing we've kind of seen it before, but the idea is, the authors are taking existing data sets, and it's really close to prompting. It really looks like prompting, where you're taking the data set, so it's the premise and the hypothesis, and they are trying to fit them in some templates. So basically, the idea is like structuring your input. Like instead of just going for raw text, if you try to structure it a little bit in a weak way, even you get better results. And here's what I think the calculus have been waiting for. I'm talking about calculus because calculus really like bootstrapping and bugging and boosting. And if you ever train a BERT model, you realize that some slight changes in the parameters, I don't know, the learning rate or the initial random point or the seed can give you different BERTs with different performance. And so we can train plenty of those, and we can use the Bootstrap principles, and we can make the predictions more robust, and we can have also, non-parametric intervals, whatever for here. Now, this is an interesting paper. It's another holy grail of transformers, like the codex. You are trying to use a language model to synthesize code, and it turns out that's not enough. Like most of the time, the code has mistakes or has problems, and you need to use a more complicated system where you're basically getting you're getting a query. You're having training exams, so you're trying to find a similar query, like natural language query, associated with a prompt, with a template, something similar code. So you use that, you synthesize your program with the help of a language model, then you try to validate and pass it basically from a compiler, see if it violates things, and you keep sending it up and down. And in the end, you get something which is more robust. Again, moving towards the direction of robustness. We saw this in a lot of papers. Robustness means, closer to production. And here's a paper that basically deals with the scalability. And the idea is that, while you're training, why do people use self-attention? They use self-attention because it's differentiable. So you attend to whatever facts you have to your document. I don't know. People have tried to go as many tokens as you can. They started for 512. I don't know. They went all the way to 10K. Now you can basically go to even more by sacrificing some parts of your model. Like, if you remove the differentiability, you can always in the self-attention do a k-nearest neighbor on other things, on cast key pair values, and use them. Instead of using self-attention where you have to have an n by n matrix. Okay, so that way you can have storage of a lot of facts or a lot of embeddings somewhere else, or like on a vector database. And the idea is a bit old. It's like 2 years old, where people worked on the technique called memorization. Sometimes they also call them non-parametric. Did we see that over here? No, non-parametric neural networks. And we had this in the presentation of ICLR 2021, where it was presented at a workshop, where basically you keep a big cache or a big database of sentences, and you embed them through BERT, and then when you have something new, you do a K&N lookup. Yeah, so this is another paper that builds on the same idea. So it does exactly what this paper is doing with an extra step, where it uses an ontology. So basically, it tries to refine the predictions by introducing, they call it structural locality. I think basically it's more or less like an ontology, or like a symbolic constraint in terms of, making better choices. So you're basically combining nearest neighbors on the embedding space and lookups on the symbolic space to improve things over there. I'm just mentioning this paper. It's not my area of research, but now people can use, again, language models or transformers for almost everything. And one of the things is anomaly detection. So, it really, I felt like when I was reading that paper that needs some work on the self-supervision part. It looked a little bit, I don't know what's the right word over here, but it wasn't very convincing. But overall, the idea is that, the anomaly is kind of like a glitch in the attention, but something anomalous in the attention, they usually translate to anomalies into your data. This is also a paper. It's mostly theoretical, but language models don't. They get you. It's a confusion. The softmax, it gives you a number. That number is not necessarily a true probability. Okay, because you really have to sum, over all instances over here. So that's like the zeta function. And here they have some approximations so that the output of the MLMs is something closer to a probability, to a true probability. Again, I made a promise that you're going to see more transformer architectures. This is kind of like a multi-resolution transformer, like a pyramid. That's why it's called the piraformer, not from fire. Like pira is from pyramid and not from fire. But here, and you see the kind of like complexity advantages that you're having. A fairly easy, straightforward architecture. This is called the COBEL, or contrastive BERT for reinforcement learning. So one way of seeing that is as kind of like BERT being the knowledge base for reinforcement learning, or holding the knowledge. Not my expertise, but I like the fact that the results were really impressive when compared to other, the major improvements compared to other methods. I mean, some of you might be familiar with this universal approximation theorem back, I think, in the 90s, where it was saying that neural networks or perceptrons, multi-layer perceptrons, can approximate any, I believe, continuous function, or even discontinuous, depending on the activation function that you're using. Now, they're trying to prove that universal approximation are a constraint. So you have like a constraint-based problem, whether this can be approximated with the transformer. Okay, it's an interesting theoretic results. That paper again is the same speed that I talked about. External knowledge bases that the transformer attends. Here, they call them concepts. You can, I think relational AI, we use a lot the conceptual modeling of the object role model. So you can really translate your concepts into vectors and only attend to them. And but that way, you might take a toll or a kind of like a small decrease in your accuracy, but bottom line is that you're getting very interpretable outcomes because all your attention is over known concepts. we're getting closer. I think I've expressed in the past, for those who know me, my preference and my interest in theorem proving, as I believe these are the most difficult artificial intelligence problems, and I have kind of like conjectured that we're gonna see techniques from theorem proving being applied to a lot of AI applications that they have to do with reasoning. So it turns out that collecting labels for theorem proving is quite expensive. According to the paper, it takes like 2.5 man years per megabyte. It's really not easy. And here you have like a set of 9 different self-supervision techniques to basically improve your results, and they see like a 50% lift in the success of theorem proving. Impressive paper. And yes, it's something really I always find it funny, but it's interesting that we've been making this mistake for so long. So as a data scientist, the first thing you do when you scrape something is use beautiful soup to throw away the HTML. But the HTML is there because it's knowledge. Okay, so it's not really we shouldn't be doing that. Like if there's knowledge, we should capture and keep that. And usually HTML is some hierarchical. It's like graph based, so it's kind of like rich knowledge, relational in a sense. And it turns out that if you use, it's kind of like an instruction, like by saying that this is a title, it's basically telling you that this is important. Like, and the language model understands that. So keeping this, these labels, the HTML markup, actually improves the results. You can see here in that like text box. So you probably didn't realize that we went to 31 papers in language models. And I'm going to stop here, the first part of our ICML 2022 presentation. And we will continue with, the second part soon. Thank you.